Okay, you can start. I will remove the previous lectures.
Okay, I'll. Okay.
Yes, yes.
Okay. How's the sound quality?
Can
anyone confirm the sound quality?
And can you hear Auntie clearly?
Nobody is there.
Yanni is there.
Can you confirm?
Yeah.
Sound is good.
Okay. All right. Sorry about this delay. Anyways, let's continue with the course. Having a look at the schedule. We are now starting week 4. Now we will have another continuation lecture. Same topic. Then the exercise 2 on Thursday. Yes. Have you started already working on the exercise 2? I suppose. Is it clear? If it's not, you can ask during the play. It should be more or less straightforward. All the details were covered in the lecture. All right, and the first midterm exam will happen in 1 week, starting at 9:15, and the rest in class. So also the remote participants should, if you are not outside Finland, you should attend the class, take the exam. All right, so last time we started with this downlink multi-user MIMO system model, and started with the definition of SIN, signal to interference plus noise ratio, came up with this formula. Now you can see this as a system of equations. We have K users that are served by the base station simultaneously, the same resource block. For simplicity, we assume here that we have just one resource block, time frequency whatsoever. So we have basically K equations. So you can write it as a system of equations. As long as you have as many equations as variables, you can resolve. If P is the variable, which depends on the case, as long as you have as many equations, in principle, you can solve the system of equations, provided that these coupling variables have certain conditions that we will discuss later on. Okay, so let's start kind of straightforward manipulation of this SIN formula, just to represent the system of equation in a more concise form. So we can start rewriting the SIN by multiplying both sides with the denominator. So we get gamma k n0 plus gamma k sum over I not equal to k pi h k I equals pk. Okay, so this applies now for all k. All right, so you have k equations, right? System of equations. Now we can Okay. All right, so without any loss of generality, we can add both sides, the missing term here. So what we get is then gamma k and 0 plus gamma k sum over all users. And so we add here the k component. Plus 1 plus gamma k k h k k squared. Okay. So now we can rearrange. Let's see. We can divide both sides by this scalar here. Assuming now that the UK sticks, so this is a scalar, right? Real value. Right? So we divide both sides. 1 plus gamma k times h k permission UK squared, right? What we get is gamma k over 1 plus gamma k h k 0 plus gamma k say the summation, and we have here effects. And then we can just denote this as AK. AK, right? Just the scalar. That's given in here. So you can see that here we have also, let me write this. You have all these variables ti times the corresponding coupling values. So if we now denote here, we denote the scalars hk remission ui as g cky. So we can collect all these terms. Let's assume the size number of users is 3. So we can collect all these terms into a matrix. Right. So we have G11, G2, G3. Then we have G12, G13, G2. 1, 3, 2. So here in this matrix, every real valued scalar corresponds to product in a product. Okay. So if we think about, let's say, just for simplicity, let's assume user 1, how we can write this system of equation as a function of, if we want to gather all these variables, p is now the variable, power. If we want to gather all these power values into a vector, right? We call it p vector, we call it one a, right? So let's consider that this is user 1. So k is 1. So we can write this equivalently as we have to do some reordering. Actually, we move this side, this to the other side. So we can rewrite this one as pk minus this term equals this, right? Okay. Should I rewrite that? Well, just take this term over here minus. Okay. Given that, we can rewrite this formula as 1, 0. Let's assume that 3 users. 1, 0, 0 minus A1. A1 corresponds to this value for the first user times G11, G12, G13 times E1, E2, E3 equals A1 and 0, right? Everybody can see this? So P1 minus A1 times the sum of G11 times P1 plus G12 times P2, G13 times P3, right? Equals A1 times N0. They are the same, okay? Now we can simply, so this is for the first user, okay? What about the second user? All right, the second user would be 0, 1, 0, A2, and then just changing the index here, G2, 1, G2, 3, A2, okay? The same, okay? So now we can all gather, so we have K or 3 of these equations, and we can gather them into one matrix equation. Something like a diagonal matrix or identity matrix minus diagonal matrix of this A's, let's say A1, A2, A3 times the G matrix G11, two times the power vector P1, P2, P3 and this equals A1, A2, and A3 times N0. Okay? So this is the same as I minus. Now we can call this as a diagonal matrix of A's, right? A times G times P vector equals okay. So in this formula now we have gathered all these K equations, right? People use it for. Now it's just like any system of equations, how to solve P, right? If you have A times X equals B, you solve X by inverting A or pseudo inverse. This happens to be always in this particular case square matrix, right? So it's inverted. Well, given that, given that this matrix here is invertible, it's not always if these rows are linearly dependent, then of course this is not invertible and the problem is infeasible. There's no power allocation that can satisfy the SI constants. Power will go to infinity. If two users are, for example, linearly dependent. Right. So we should remove that. Okay. Right. So basically, we can just solve the power allocation. So if we have a question, but we will discuss that later on. If we have a fixed SI and R, and we want to find a power allocation given these fixed beamformers, fixed channels, what would be the feasible power allocation such that all users satisfy the SI and R constraint? That's what P from here. Okay. All righty. So that was the downlink. Now we can rewrite let's reverse the roles. We have 3 antennas here and 3 users. Okay, so we now consider the downlink model. And we have downlink beamformers U1, U2, U3 specific to each user. And then we have these corresponding channels. Let's now, just for fun, reverse the role of the transmitters and receivers. Okay, so now we have 3 single antenna transmitters accessing a multi-antenna base station in uplink, right? With certain powers, Q1, Q2, and Q3. Okay, and then again we have a set of SIRs. Okay, let's start with the system model. So the received signal model here is a summation of all users I, xi. So xi we can also split to like power allocation pi and normalize it. It's a simple deal. Okay. Now we can write sorry, qi plus noise vector. Okay, and we can write this one concisely in a matrix form. Just stack all these channel vectors into matrix. But if you have 3 antennas, 3 users, that would be 3 by 3 matrix. H1, H2, H3. H matrix here, and then we have the power loading matrix. Where this is the diagonal matrix times the vector plus the noise. Okay, now we would like to detect one of those symbols, Ti of K. So we can write that we have this is an estimate. The output of the beamformer is optimized for user K. Okay. So we can write this again. So we can pick the K user. We have UK and HK. UK, EK plus. So this is the desired part. This is the signal, desired signal. And then we have the interference, I not equal to K, U, K, permission, H, I, Q, I, D, I, plus the noise at the output of this PCB form. Okay, this is the equivalence system model. Question? it seemed like you were lifting your hand. Be careful. Outrageous. You are allowed to ask questions, by the way. Anyways, put the G over there. So now we can compute the signal to interference plus noise ratio again in uplink, right? Gamma K uplink. Again, that would be the expectation of SS complex conjugate over expectation of I plus N, I plus N. Okay. And we plug this in here, we get following expression. So we have QK times UK remission HK square and sum over I UK remission HY square plus UK norm 0. Okay, if we make further simplification that or assumption without affecting the SI enough, you can assume that UK normalized. Right? So it's a unit norm. It doesn't affect the SINR at all, right? Because both sides are scaling the same norm. So we can, if we make this assumption, then this becomes 1, right? So we can remove this. All right, this is the SI line uplink. A bit different than here in the slides, but they are equivalent, right? Because this is a real valued scale up, right? So we can change the order here. So we can, this is equivalent. So UK remission HK is equivalent to HK remission UK, right? So this is what we do here. We just switch the indices. Okay, and we end up with that model. All right, so we have now the SINR expression in the dual uplink, and you can see that it has the same terms here as in the downlink, right? The same G terms, right? We defined G. Same for the normalized U, same G entries, the G matrix appear also in the uplink formula, right? The powers are different, okay? But these coupling values, I call it coupling matrix. If G is diagonal, there's no interference. You see this? If G happens to be diagonal, there's no interference between users, like a zero forcing solution. If you make U to be the zero forcing beamformer, its off diagonal terms disappear, right? Or if HK, all HK happen to be orthogonal to each other, and we use match filter. Again, diagonal matrix. Okay, no interference between users. Neither in output or down. This is, in general, these off-diagonal terms are not zero, right? So there's some coupling between users. We should find a good balance between the diagonal term, which is the desired, and the off-diagonal, which is undesired, right? You see, for the user 1, this is the desired term. These are the interference terms. For user 2, this is the desired term. These are the interference terms, right? Interference from user 1 to user 2, interference from user 3 to user 2, interference from user 1 to user 3, user 2, and this is the desired of user 3. Okay. All right. So now we have these SINR formulas for both uplink and downlink. We can do exactly the same steps. Right, so this is uplink. We can do the same steps as in the downlink. We can multiply both sides with the denominator, add the missing term, right? So we get this 1 plus gamma k. Right? Exactly the same expression, right? If gamma k uplink equals gamma k downlink, this would be equivalent to k. Something that we will assume later on. And again, you can write the system of equations in terms of G matrix. So let me just again consider 3 users and the first user, right? The SINR expression for the first user. So you can write it as 1, 0, 0 minus B1 times D1, 1, D2, 1, D3, 1. Right. Now in the uplink formula, think about this user here. The interference propagates over these different channel indices, right? Received at the output of the beamformer, which is dedicated to user K, right? So the channel index changes here, right? In the downlink case, the beamformer index changes, right? In the downlink, we're going to be received signal at user 1. We have a broadcasted signal that propagates over the channel H1, and the broadcasted signal is a superposition of all beamformers. Right? Sum, you recall X equal to sum over UI, right? So now if you look at that received signal at user 1, the channel is the same, but the beamformer index changes. In the uplink, if you look at the SINR, the beamformer index is the same, it's a user specific, and then the interference is coming from different signal than users, so the channel index changes. Okay, maybe you have to think that a little bit. So equivalently for user 1, we can write this SINR expression as like this. Okay. So now for user 1, we have picked G11, G21, and G31, which happens to be the first column, right? Images. In the downlink case, we pick the first row. Okay. So now we can reuse this G matrix. Right, when we take the transpose of the G matrix, the columns becomes rows and vice versa. Okay. So we can rewrite using still the same G matrix. We can plug in. Basically, we can again write one, two, three. There we have G11, G1, G2, G12, G2. Okay. So this matrix here happens to be transpose of this matrix. Everybody can see this? Times 1, 2, 3 equals right. So this identity matrix is the diagonal B sub B matrix. This is the G transpose matrix. This is the uplink power allocation vector Q. This is the vector of B's. Right. We have gathered all these uplink SINR formulas into this one matrix. Okay. And again, you can see that the uplink SINR depends for the fixed beamformers U, normalized beamformers U, either used in downlink or uplink. Both uplink and downlink SINR formulas depend on the same coupling matrix G. Right. In downlink, the G matrix, uplink, the G transpose matrix. Right. If you can understand it from the setup that in the downlink, the interference is broadcasted over the same channel, right? The interference is from different beams, right? In the uplink, the interference is unicasted from all these single antenna users and received at the same time at the beamformer at the output of a user-specific beamformer, right? So the interference is now in the channel indices, right? Interference is channel indices in uplink, in the beamformer indices in the downlink, right? That's why we have this transpose behavior. Okay, so both V and Q we can solve from these equations. So something quite exciting happens when we assume now that the SINRs are equal in both downlink and uplink. So we set gamma k downlink equals gamma k uplink. Okay? NDP for all users, for example. Okay? So therefore, A equals B, right? If we look at the definition of A, it depends on the SIR and then the GKK here. So AK equals BK, then gamma K equals gamma K uplink. Right. So now we can write the sum power expression first for the downlink. A couple of matrix tricks that we have to use to show this equivalence. So fine if I write directly here.
Yes.
All right. So some power in the downlink, obviously it's just sum over all users. Some power. Equivalent to multiplying the power vector by one vector, right? This is equivalent to P1 plus P2 plus P3, right? And now we just plug in the P expression here. So this is the P expression. Okay, so we did here minus 3. Yeah. Okay, right. You can rewrite this one, for example, EA times EA inverse minus G inverse. Okay. Now this is equivalent to inverse for square matrix. Okay. So this is equivalent to multiplied by A. Now this is equivalent to EA inverse minus G inverse times EA inverse times A. Okay. And obviously when we multiply, say 1 over A1, 1 over A2, 1 over A3 times A1, A3 is same as 1, 1, 1. Okay. Simple trick that we did. So equivalent of this. Clear? Right, so now we plot that rewritten formula E here. So we have this matrix here, matrix inverse, which is multiplied by one vector from both sides. Right, so this is just on scalar value. Right? So we can, without changing anything, we can take a transpose here. The sum is still the same, right? Because what we do here is basically we just sum up all the entries of the matrix. That's exactly what happens. Here, multiplying a matrix by one vector from left and one vector from right is equivalent to summing up all the entries of the matrix.
Or we can transpose all together.
Sorry?
We can transpose all the term because it's constant, right?
Yeah.
Ideally the same.
Yeah. First, we just take this transpose of the whole matrix, right? And then we can use the rule, matrix rule. Let's see, take transpose of inverse is the same as inverse of transpose. Okay. So we interchange this to here, right? So then we have EA inverse minus G transpose inverse. Okay. Now the transpose we can take separately for both. Okay. And transpose of a diagonal matrix is diagonal matrix, doesn't change anything. And then we can take this transpose there. And we get this is the expression here. Right? Which is equivalent to Q. Okay. Q formula. So multiplying a Q vector by transpose of one vector from the left is equivalent to summing up the powers. So given the same SI constraint and the fixed beamformers, U, normalized beamformers, the transmit power, some transmit power, not the individual Q and P, but the sum of transmit powers in downlink and uplink are exactly the same. Right? It's just simple math steps. So this is something that we will use in the following steps. Okay, this is just a summary showing the equivalence of the downlink gap is dual uplink. So in the downlink, we have multiple symbols that needs to be broadcasted to multiple users. So broadcasting means that we are taking a superposition of all these transmitted symbols multiplied by corresponding beamformers superposition, summing them up, and then we form the vector X that is transmitted from all downlink antennas, base station antennas, and now propagated over the channels that are now collected into this matrix H remission, where each row corresponds to user-specific channel. And then at each user, we add noise, independent noise, and get the received signal per user. Okay. Assuming reciprocal channel, in the uplink, we have k signal on the users. Each user generates a single symbol with a combination M, X uplink 1, X uplink K with power Q1 to QK. Now this is received at the base station. Each signal propagates over the user-specific channel, and then we add noise at the base station antennas and get the received signal vector Y uplink. And now from this multi-axis channel, or from this complex values vector Y, we can dig out the desired symbol by beamforming. Right, so we assign U1 to the 1 to K, or capital K, and we get an estimate of transmitted signal. Right. So if the channels happen to be orthogonal, we can use match filter here, no interference. If we apply zero force in here, no interference, the G matrix becomes diagonal. If we apply MMSC, the diagonal terms and the noise are balanced, right? We try to make these off-diagonal terms more or less the same level as the noise. That's the general rule of thumb. Okay, so you can suppose, given the fixed beamformers, you can express the SINR, like this is equivalent to U HK Hermes and UK, right? This is HK Hermes and times UI. This is the SINR form, the same SINR form, just replacing these vector products with the scalars. And you can plug that in here, and you get a linear program, right? So you have a linear objective, K linear constraints. And you can express also in the canonical form, like this. This is, of course, summing all the powers. This is the SINR constraint matrix. Right. Now we have to relax the equality with inequality. Be able to pose it as an optimized problem. But for sure, at the optimal solution, the inequality constraints hold equally. Right. If there is any constraint which is loose, meaning that the actually there's a mistake again.
Oh, this has been there many years. Okay, I'm gonna fix it right now. It's, otherwise, it will persist. I have said many years that I should fix this, but I haven't yet fixed it. So let's fix it. Where is it? Where is it? Sorry to take your time. No, it's over here. Here. Right. Voila. Fixed for the next generation. Fixed here as well. Yes, excellent. All right.
Okay, so meaning that if there is any SINR which is not tied after optimizing, meaning the actual SINR is larger than the SINR target, it means that we can reduce the power for that user, right? So they're in conflict. The objective and constraint are in conflict. So you can always reduce the power to the point where the actual SINR and the SINR target will be power. So we can for sure, without any doubt, replace this inequality with equality. Right? So when we have and replace this with equality, then we have a closed form solution. If the gamma target is feasible, meaning that there is a finite power that can reach this gamma target, we can solve key just by inverting this matrix. Feasibility means that this matrix has to be invertible. Not invertible. If it happens to have one zero eigenvalue, then it means that it's inverse infinity, right? Meaning that the power goes to infinity, right?
Okay, let's take a 5-minute break and continue. 20 past.
Okay, so here we have assumed that the beamformer is fixed, optimized powers. Okay, what if we still consider this uplink problem? Okay. Maybe I should update this. It leads to downlink bandwidth optimization, but let's just imagine this is the uplink problem. Okay, that we want to optimize both uplink powers Q and the receive beamformers UK jointly, right? So it's not obvious when we plug in the SINR into the formula. It's not obvious that this is a convex problem. Product with Q and U, but it can be reformulated in a way that can be shown to be convex problem. Don't worry about that. We will discuss this much more the next slides when we discuss linear beamforming in more detail. But it can be shown to be convex problem. So it has a single optimal solution, right? Global optimal solution. So now, typically, when you have two sets of variables, one approach to solve it is to use alternating optimizers, right? You fix one, optimize other, fix the other, optimize. You alternate between optimizing variable set 1 and variable set 2, right? So we have here QK, K, capital K values of Q, and then capital K beamforming U. It turns out that this alternating optimization happens to be iterated. When you do this iteratively, goes to the optimal solution. Okay, here we are not yet discussing about why it works like that. We will discuss that a bit more in detail in the downlink beamforming. But I just give you an intuition, right? So if the beamform is fixed, there's a closed form solution, right? If beamformers are fixed, we can just use this equation 4.13 to get optimal Q. Okay. Then for fixed Q, we could actually write a Lagrangian and do some tricks and minimize the Lagrangian with certain tricks to find U, which appears to be actually a scaled version of the MMSC receiver. Right? You can do the calculus. So the intuition here is that for a fixed Q, the MMSC receiver is the one that maximizes the SI, right? Minimizes the MSE. Right? You recall that there's this relation between MSE is equivalent to 1 plus SINR, MSE of K. You minimize MSE, you maximize SINR. That's that. That's why the MMSC receiver is also SINR maximizing receiver. Okay. Using any other receiver, an MMSC would, given these fixed uplink powers, would give you a smaller SINR, right? So if you want to minimize the power, right, you have a certain powers that are not optimal, right? Then you want to find a best possible beamformer for that maximizes SINR. Then it's simply if your SINRs at the output of the when you compute the SINR at the output of the MMSC filter, if those SINRs are much larger than a target, you can simply scale all the powers down, right? Any other beamformer would let you scale those powers less, right? That's the intuition behind why to use the MMSD filter. Actually, this is a bit misleading. Power minimizing is used for fixed powers Q. So if the powers are fixed, then there's nothing to minimize in that particular step. It just indirectly leads to minimizing the Q. When we recompute the Q for the optimized beamformer, right? So this is the intuition here, that you start from some random beamformers that are not optimized at all, and then you compute the powers Q that meet the SINR constraint, and the powers can be quite large, right? Now you plug those powers into the SINR, the MMSD, you get a result such that the SINR is actually much larger than what you assumed, but what you optimized it for, right? You normalize it, you re-optimize the powers, so the powers keep decreasing. For sure, it's guaranteed that after the MMSD update, the powers will go down, right? Because those are, it's always, MMSD always improves the SINR, meaning that you can decrease the power. So every step is guaranteed to have a monotonic decrease of the object. Right? And you can prove the convergence using the standard interference function arguments. Much more details in this book. That's how it goes. In fact, so you can do this alternating in an alternating manner, optimize the beamformers, solve the powers, optimize the beamformers, until there's no change in the object. Now we can also solve this problem in so-called joint update method. This has nice intuition as well. So when you look at the SINR in uplink, you have HK permission. Now when you plug in here the optimal MMSD, SINR, yeah, and this was your over, right? Get the SINR expression. You plug in the optimal MMSD into the SINR formula. We do the required steps. I not equal to K, I in right. This is the SINR expression. So this joint update method is basically you can assume in your SI uplink SINR that you use MMSD directly. You just plug that into the SINR formula. So then the SINR just depends the other SINR for user K. So this would be now when you multiply this by QK and you add similarly the QK. The numerator. Right, so this is the current SINR given this power QI, QK. So you can now write this as the ratio between your target SINR and the current SIR given these non-optimized powers. So this is a simple ratio, okay? Meaning that if this ratio is smaller than 1, meaning that you are not hitting your target, you have to increase the power with that ratio. Okay? So you can do this simultaneously for all users. Right? All the powers are fixed. You just compute these SINR values for each user, and you update corresponding user-specific powers. Okay. Go back to computing the SINR for the updated powers. The ratios actually are smaller, or they gradually start approaching 1. Right. So in the end, when this iteration converges, this ratio becomes 1, and there's no change in the powers. Okay. And again, this convergence can be proven using this standard interference function argument.
Right, but let's not get stuck at this.
Okay, so now we covered these linear strategies, and we will be discussing, because that's the
First glimpse at the linear beamformer optimization now for this dual uplink, which is power and receive beamformer optimization. We'll be discussing much more about the beamformer optimization in the next, after the midterm, slide 5, which I will hopefully make available during this week. A couple of simulations missing.
So in uplink we have the linear receiver which we covered here, but then we have the non-linear approach. This is the NMS system. So what about the downlink? What would be the equivalent strategy? So we already covered in wireless communication 2,
when we have the single antenna
single antenna transmitter. We draw this. Okay, we have a single antenna, and now we have a user 1. Then we have a user 2. It's 2. And then we have user 1, which is
further away, right?
the user 1 is
Further away from the base station than
user 2. Okay, meaning that H2 H2 is larger than H1, right? So now the superposition coding plus successive interference cancellation strategy was such that the first assign the rate for user 1 such that we assume that user transmission user 2
seen as interference at user 1. Right?
So the rate of user 1 is then log to 1 plus H1 square T1 H1 square. If now we are just transmitting superposition X, which is X1 plus X2.
right? We are transmitting a superposition signal. X1 plus X2. X we can split into the power and the data. So if you look at the received signal for user 1, that would be Y1 equals H1 X1 plus H1 X2 plus N, right? So this is the desired part, this is the interference. Right? That's where it comes from, right? Okay, now assuming this ordering, when we look at the let's say the SINR or the rate for the X1 at user 2, this would be log 2 plus X2 E1 and 2. Okay, and this is actually larger than this. It means that if user 2 now wants to decode the message intended to user 1, it's possible because this achievable rate is larger than. So the rate that we have assigned to user 1 based on this interference here is achievable also at user 2. So user 2 can also decode the message intended to user 1, right? But that's not the case for the reverse order, right? If we reverse the order, it doesn't hold. Here you can imagine that if H1 is 1, right, N0 is 1, T is 1 and 1, so this would be half, right? So if H2 is 10, much larger, right? Okay, and then R2 is simpler because now we can remove. If you look at the signal, received signal user 2, that would be H2 X1 plus H2 X2 plus N. N, right? N2. So here is the desired part S. This is the interference, right? But now, since the user 2 can decode this one, assuming this is interference, it first decodes it and subtracts. So the message intended to user 2 can be received interference free rate plus 2 1 plus okay. This is the superposition coding plus successive interference cancellation. And this extends to any user K. What about if we have now multiple users? Sorry, multiple antennas. So clearly we cannot. Well, we can have, of course, ordering based on norms, right? The norm of one channel can be larger than and so forth. But now, if you're applying, so that would be the fact for the match filter case. If you just apply match filter, the beamformers are fixed based on the match filter. We could still have the same ordering, right? But in general, when we look at the received signal at any user K, okay, let's still consider that two user case. If you look at the received signal, user 1, we have H1
permission times U1 times okay, E1 plus H1 U2 E2 plus noise, right? These are the scalars. This is the G11, the G12. If the beamformers are fixed, then we have strict ordering, right? We can compute this value. Well, this is actually this square. Okay. If we square this, we get G1, G1. So, so if the beamformers are fixed, we can find which term is larger, right? But if we make the beamformer variable, the ordering depends on the value that we assign to the beamformer, right? So value, if you think about this value, it can range, if we assume normalized beamformer, it can range anywhere between 0 and H, K, right? You can see this. If UK is designed in a way that this, like a zero forcing, so this goes to 0, massive, then it's this, right? So it can be anything in between, right? So there's no strict ordering anymore as in the single antenna case. So the ordering depends on the beamformer, right? So we cannot use anymore in general the SPC plus SIG strategy. Only if the beamformers are fixed, then it, of course, collapses the same single antenna. So no natural ordering of users. So in uplink, we have the nonlinear MMSC SIG. This is the optimal receiver strategy. The downlink, users cannot cooperate, right? So in uplink, we receive all the messages at once, so we can process them whatever order. We can use MMSC SIG. We can decode them in any order that we want, right? Given that the rates at the ordering. In downlink, the users can cooperate, right? They are geographically apart. So we have to pre-cancel part of this interference, unlike in the uplink. Cancellation happens after receiving. The downlink cancellation happens before transmitting. So that's called pre-cancellation. Okay. There's a lot of relevant literature. I'm not asking you to read these papers. Just for a nice to know category of this course. For some reason you want to work on this nonlinear downlink strategy, you can have a look at these early papers. So you can see that most of these papers were published in the early 2000s. Before that, we actually the capacity optimal strategies for downlink were not known. Right? First one that came up with this structure was this Sekakaya. And there were many follow-up works. Somewhat parallel, different angles, describing how the uplink downlink duality can be used to solve some capacity of the sum rate, and then the whole rate region. Of course, they didn't have yet the proof that the whole rate region of the downlink can be also computed using the uplink downlink duality, and later proven in this quite complicated paper by Carl and all. Trans IT. All right, this is just a kind of background. If I'm not asking you to read these papers, so I'm just in this course. My intention is to give a basic intuition how this 30 paper coding idea can be used for this downlink transmission. So the basic concept is quite old, not that old. First introduced by Costa, writing on dirty paper, very simple paper, easy to read, just a couple of pages. So the dirty paper coding means that, or is a technique that allows non-causally, meaning that something that depends on present and future symbols, basically interference which is caused by the same transmitter. Interference to be pre-subtracted at the transmitter without power increase. So if you think about this communication model, this is general. So we have received signal Y, which is now the superposition of X, which is the desired signal, and then we have some interference signal S. Now this is just for simplicity, it's a real channel, and this X is a vector that contains all n transmitted symbols in time. So we have the desired signal, and then there's some interference signal, which is known. Interference which is generated also from the Gaussian output, and then Gaussian noise at the receiver. So if we want to communicate, if you know S, right, at the transmitter, we want to communicate to the user such that it does not see the interference. Yes. So one very simple strategy what we could do, that we could assign X to be equal to U minus S, right? Oh, it would cancel, certainly. It would cancel the S, so the receiver would not see it. But the problem here is that if S is large, it has a huge power penalty, right? Just for nothing, we would need to send a large X just to cancel this S. To send this desired signal U to the user of interest. And at the same time, if this S is generated by the same transmitter, like a broadcast channel, this transmission would also cancel that other transmission, right? So if this S was intended to another user, this transmission to another user would cancel also the transmission of the originally the other guy that we want to serve. So of course this doesn't work, right? It's just a nice example, also discussed much more in detail in the book. By the way, I recommend to read the book. It's quite self-explanatory. So the question is that, can we have a method which can be used to pre-subtract this known interference without such power increase, that, for example, using that naive scheme.
So the theorem given by this Costa guy states that if the transmitter, but not the receiver, has perfect knowledge about this interference generated at the same source, then the capacity of the channel is the same as if there was no additive interference at all. So let's see how this works. Just to, before we go there, let me just give you a brief recap of the square packing idea to show to derive the capacity of AWGN channel. So let's ignore the interference first, right? So we have y equals x. These are n-long vectors, right? It's like y equals ym equals xm plus wn, right? But we just gather all this. All this n into n-long vector, okay? Then we can use this square backing idea is that if we have this if we now project this n-dimensional vector y to 2, just consider 2 dimensions. That's basically the length of the vector. That would be simply 2 norms. Right? It's the radius. This would be the y sphere. The question is how many of these noise pairs, right? So we assume that there's we want to find out how many messages we can send over this n transmit intervals that gives us the rate bits per second per hertz. So you can express that as a ratio between the y volume and the noise volume, right? So in general, if when the length of the y in general, we can express y as y1, y2. But we have, of course, all these cross terms there. Oh, no, this is the next. So, okay, cross terms actually. When you plug in now that y equals x1 plus w1 Of course, we have all these cross terms here, right? But now when n becomes large, all these cross terms kind of vanish with respect to this x squared and noise squared terms. So we can approximate this as n times e plus we assume that x follows
exponential Gaussian distribution with variance p and noise also Gaussian with variance sigma. Right? So this is the radius of the vector. Okay? And then similarly for the noise, okay, we have only noise there, so n times sigma squared. So now, when we want to compute the volume of a sphere with n dimensions, it's in general, it depends on the radius of the sphere, which is given by the norm plus square our exponent with exponent n and some constant in front divided by now the square of the noise all right, this is the number of, so this is the volume of this y sphere that depends on the radius of the y, which can be, this becomes deterministic when n becomes large, right? So we can express that, okay, how many of these noise spheres we can fit inside the y sphere, meaning that how many messages we can transmit without interference, right? Meaning that interference would mean that, you know, these spheres would be overlapping. Spheres are not overlapping, there's no error, okay? One sphere would correspond to one message, okay? So this is the number of messages, and now we can express that in bits, and then normalize over n. Right. So this would be the rate. So now when we start doing the math, we can of course take the exponents inside. So we have 1 over n log 2. These they cancel out. N plus sigma square n sigma square square root times n. And this we can take in front. The n cancels out, and then we have off here, and n cancels out, and in the end we have log 2 plus SN. Okay. That was the argument for the sphere bracket. And this is for the real case. So if we have a complex valued channel, then we get one extra dimension. We get I and Q, phase and amplitude. So we get 2 times half, right? So the complex Gaussian distributed signals, we get expression without that half. Okay. All right. See how much we can cover this. So again, we assume this, for simplicity, we assume the single antenna transmit the signal to the receiver. And we assume that in receiver applies a linear filter alpha, which is designed to minimize the mean square error between transmitted signal and the received signal. Let me just, before we go any further, just rewrite quickly. Scalar alpha. Alpha is now a scalar receiver, right? But we can extend that to vector case, then it becomes MMSC beamformer receiver, right? So we would like to find a we have an x hat minus x, right? This is the mean square error between the received estimated signal and transmitted, right? And then the estimation happens at the output of this optimal scalar filter. Mean square error. Now let's assume that there's no interference for simplicity. So we can plug in the expression expectation alpha times x plus alpha times w Okay. So when we now expand the square term and take the expectation, all the cross terms again disappear. So what we have is alpha alpha times n square plus alpha minus 1 alpha squared, okay? N times t. Okay? When n is large, right? Approximately. Okay? The norm, these are vectors, right? When n is large, you have a Gaussian vector where each entry of that vector follows Gaussian distribution with certain variance. Then when n becomes large, this noise vector can be approximated by just the number of entries in the vector times the variance, and similarly for the noise. Now when you differentiate, now alpha is the optimizer variable. You differentiate this with respect to alpha, you get 2 times alpha n sigma square plus 2 times alpha minus 1 times n p. Set that to 0, 2 cancels out, and then you have get alpha, which is the side. We have this e plus. Okay, this is your optimal schema, right? And you can see that when P becomes large, SNR becomes large, or noise goes to becomes small, alpha becomes 1. Okay. All right. Let's take a break now and continue tomorrow. I will then go quickly through this dirty paper coding argument, the extended alpha-based idea, how we can choose the transitive vector given the knowledge of the interference vector, extended alphabet, and choose the point in the extended alphabet point that is close to the original x, like a vector sum, then transmit the vector, but then transmit x1, which is the sequence between the alpha and the, and that leads to the solution where as if there was no interference.
And we will continue tomorrow, 10:50.
Okay.